and you ask your friends to join now. I've also have written in our chat group. Today I'm a bit busy about this mark submission process that is going on in university portal, and today is the last day. So maybe I'll not be able to stretch longer for this particular class. I have some works to do, but yet I don't want to miss the class because completion of the syllabus is also very important, and your final examination is gradually knocking at the door. You keep track of your semester fees and the clearance of your semester fees and the examination form fill up date. You just keep track of these things so that you shouldn't miss it. Okay. And if you have any problem regarding that issue, any major problem, then you can contact me through CR, or you can directly WhatsApp me. If you have any issue regarding MOOCs, then you can contact NKR sir. And the data which I collected day before yesterday regarding the mentor-mentee, that has already been submitted to the Makeout portal, but you will not be able to see it because Makeout has actually generated a separate portal for submitting those data, which is not open for students. So I don't know, maybe in future they will give you access to view what information has been uploaded over here against your roll number, but the process has been done. I have uploaded from the data from starting from roll number 1 till roll number 33. Rest of the data of mentor-mentee will be submitted by the other coordinators. So this is the status. Now let us come back to our topic of today's class. Our topic of today's class is based upon another very useful technique of hypothesis testing, which is called chi-square test. Now here, this word, sometimes I have seen students to pronounce this word in a wrongly fashion. Once a particular students pronounced it as chi-square, but it is not chi-square, it is actually called the chi-square. And actually this particular name has a notation which is written in the following manner. So we can write this as chi-square. This is called chi-square, okay? Now, the definition of chi-square that I'm not going to discuss right now. Chi-square is a kind of random variable. It has some sort of probability distribution. The form of the probability distribution will be explained later on. Today, I'm going to use this chi-square distributions, use this chi-square distribution in hypothesis testing. And I'm going to show in what situations this is used. To be very brief, at least I can say for today's class that you know that if capital X is a normal variate, we can standardize this normal variable into the following form. We can define a new variable capital Z, which can be written as x minus mu by sigma. We all know that. And we know that capital F, if capital X is the normal variable with mean mu and variance sigma square, then Z is the normal variable which follows the normal distribution with mean 0 and variance 1 or standard deviation 1. Now, if someone take the square of this normal variate, suppose I write Z square instead of Z. So that will become x minus mu by sigma whole square. Or meanwhile, I must say that the chat box is closed. I will deactivate the chat box before the end of the session, not now, because it gives me a distraction. Now, x minus mu by sigma whole square, if I take the square of this standard normal variable, we get this expression. This is actually your chi-square variate. This is known as chi-square variate with 1 degree of freedom. Okay, and suppose there are two normal variable x1 and x2. Okay, x1 follows normal distribution with mean mu1 and variance sigma 1 square. X2 is a normal variable which follows normal distribution with mean mu2 and variance sigma 2 square. Now, in this case, we can define two standard normal variable in the following manner. We can write Z1 as x1 minus mu1 by sigma 1 and Z2 as x2 minus mu2 by sigma 2. Now, if I take the square of this standard normal variable, we will get this type of things. And if I add this Z1 square and Z2 square, then this is another chi-square variate with 2 degrees of freedom. 2 degrees of freedom. So this is all about chi-square variate. See how uninteresting this. When I'm saying these particular things to you, you have come to know that, yeah, this is called chi-square, but we don't know how to apply this knowledge of chi-square to different problems based upon different types of situations. So first of all, let us learn how to apply this chi-square variate in fact. What is the practical application of this chi-square variate, chi-square distribution? So that's why I have chosen to start from the problem, start from a situation where I am going to explain how chi-square is used. Let me erase it first of all. Situation. So first of all, let me read what is written over here, and then I'm going to explain term by term. We consider a very large population and suppose that each member of the population has a value that can be 1, 2, 3, and so on. For a given set of probabilities, if there are small k number of observations, so there will be small k number of probabilities for each observations. We'll consider the testing of the null hypothesis that this probabilities represents for each I a proportion of the population that has value I. Now, if population proportion is the random variable, so ith value of the population proportion is capital Pi, then this small pi will be some value of this capital Pi. So capital Pi is the name of the variable, which is the population proportion or probability associated with the population, and small pi is somewhat some specific value of this population proportion. That is the difference between capital Pi and small pi. Just like when we test the hypothesis, we consider mu to be the population mean, and one of the specific value of mean is, say, mu naught. Suppose mu naught is 0.65. So if I write this as null hypothesis, what is this? This is just the name of the variable under consideration. What is that? It is called the value of the variable under consideration. Okay, so that's this. In the same manner, this small pi is the value and this is the variable under consideration. Okay, hope you have understood what I'm trying to say to you. Now this part is clear. Let me proceed. So thus, if we let capital Pi denote the true proportion of population, true proportion of population that has value I, for each of these probabilities, we are going to test the null hypothesis as follows. Null hypothesis that this population probability is taking the value small p1, this population probability taking the value small p2, this population probability taking the value small pk. So actually, if you try to recall that in Z test of single proportion, we actually used single proportion, and in two population theory we used the difference of population proportion. Here we are actually going to test the multivariable type of case. At a time we are going to consider several population proportions and their individual values are hypothesized, and we are going to test it against the alternative hypothesis that each of these population proportions are not having the values as specified by me. And each of these population proportions corresponds to each of these items in the population. In such a case, the test we use is known as chi-square. So see the definition of chi-square that I wrote in the above case, and the situation of chi-square, it looks very dissimilar to one another. In the definition, I talked about the square of the random variable, square of the normal variable. In the situation, I'm talking about the characteristic of the single proportion or multi proportions of the population. But if you think deep, you will find that there is a very little is very fine connection between the two. In single proportion case, we used Z test, the standard normal variable test. And here in this multivariable case, we are actually going to take into consideration the square of the standard normal variable case. But although the form of the statistic that we are going to use will be something different, which has been deduced from the actual definition for the sake of its usage in the situation. Okay, so let us try to find it out. You will get to see the connection between the two gradually. With respect to the situation that I have defined, here is an example for you. It is known that 41% of the US population has type A blood, 9% has type B blood, 4% has type AB, and 46% has type O blood. Suppose that we suspect that the blood type distribution of people suffering from stomach cancer is different from that of all overall population. So that is the study, under consideration. Blood group A, blood group B, blood group AB, blood group O has been considered. There are other blood groups also, very rare. Okay, now AB has different types, AB positive, AB negative, B positive, B negative, A negative, A positive, O positive, O negative blood group is also there. Apart from these, there are other blood groups also, very rare. So they want to study whether the people suffering from the stomach cancer, they will not actually falling into this category of blood groups. For the stomach cancer, the patients suffering from stomach cancer are actually falling into the different categories of blood groups. So that is the point under study, and they have actually made a pie chart like this, showing the percentage of people having a specific kind of blood groups. Okay, this is the situation that I'm actually explaining over here. Now, what do we want to know? We want to verify that the blood type distribution is different for those suffering from stomach cancer. But in null hypothesis, what have you assumed? We have assumed that population probability 0.41 is true, population probability 0.09 is true, population probability 0.04 is true, population probability 0.46 is true. What does this mean? This means when you are considering a patient of stomach cancer in the population, he is a part of the population. Now, this population, I am considering that in this population, only this type of blood groups are present. This percentage of blood groups are present in this population. Now, if I am going to accept the null hypothesis, I am going to conclude that, yeah, the patient is who is suffering from stomach cancer, he is one of them. Either he is a blood type A, or he is a blood type B, or he is a blood type O, or he is a blood type of AB. But if you are going to reject the null hypothesis, what does this mean? This means he is not of any of these above blood types. His blood type is something different. Okay, so that's why this null hypothesis will be considered in the following way. Now, if I just write P1 equal to 0.41, P2 equal to 0.09, P3 equal to 0.04, and P4 equal to 0.46, and if I don't explain what does it mean, then there is no point. So here is the explanation for you that I have given just now. Okay, then I'm going to continue my reading. P1 is the proportion of all those with stomach cancer who has type A blood. P2 is the proportion of those who has type B blood. P3, the proportion of who have type AB blood, and P4 is the proportion who have type O blood. general rule is there to test the null hypothesis. This is a specific case, okay, according to our situation. But in general, if I consider there are k observations, so in general, the null hypothesis will take the following form. Here we have 4 observations, so 4 probabilities. Here there are k observations, so k probabilities. Step number 1, we need to draw a random sample of elements from the population. Suppose this sample is of size n. Okay, now there is this statement looks very simple, isn't it? The step 1 looks very simple, and actually not much time is dedicated to explain this particular scenario. I do not have the time to discuss this in detail, but at least I can say that this part looks very simple, but it is not like that, as simple as it is. The sampling procedure will come into play. What type of sampling procedure you are going to use over here? Are you going to use the cluster sampling? Are you going to use the multi-stage sampling? Are you going to use the simple random sampling? Are you going to use the purposive sampling? What will be the source that you'll try to get hold of to get the sample data? Okay, all these questions are actually very relevant over here. But therefore I wanted to tell you that this line, although looks very simple, is not very simple. This is a huge task of gathering all the information related to sample from the population. What should be the proper sample size? How many sample data we must consider? That is also a very important question. Okay, so suppose we have come across this hurdle, then we'll suppose this part has somehow been achieved, and then we come to this particular stage, step 2. Let capital Ni denote the number of elements of the sample that have value I. Okay, fine, no problem. So, okay, sorry. So now you see this Ni is the number of elements. What type of elements that this Ni is actually representing? We have some sort of characteristic. We have some sort of characteristic in the population. Now this Ni is actually representing the number of people having that characteristic in the sample. Okay, so that number is given by this. So once the sample is collected, this number is a matter of some time to obtain. We have gathered all the information in the sample data, so we can also find out what is capital Ni. Step number 3, if H0 is true, that H0 we have actually designed over here, then this capital Ni will be a binomial random variable with parameters n and pi. This is a theory. Okay, this is a theory that has been written over here. Okay, for each I, let ei denote the expected number of outcomes that equal I when H0 is true. And you know the expectation is given by, in binomial variable case, the expectation is given by ei equals to n into pi, isn't it? So they have calculated the expectation. You can calculate the expectation. Once you calculate the expectation, what you are going to do, this is the observed values, capital Ni, the number of people having that characteristics that you are actually going to study from the sample. This is the characteristic that you are observing directly from the sample. Suppose you have collected 20 cancer patients. Out of these cancer patients, some has throat cancer, some has lungs cancer, some has colon cancer, and suppose 3 or 4 people have stomach cancer. So that 3 or 4 is your capital Ni. This ith sample, the first sample that you have drawn of size 20, it is the this number 10 is so number 2 and 3 is the required number. This is called N1. Another person, he has gathered 30 sample, and if I fix the sample size to n, then okay, he is again gathering the same number of 20 samples from different. Suppose you have gathered your information from Chittaranjan Medical College. Another person has gathered his information from Thakurpukur Cancer Hospital. Another person has gathered information from that cancer hospital that is situated in Rajarhat. I forgot its name. So these are the different sources and you have gathered different samples. Okay, and you are observing this data ni for different samples. But what is the expected number of samples? This is your observed values. This is your hypothetical value. So expected number of sample mean expected number of persons that you that can be that you are expecting to have in the sample. This number will be different from the observed number. Okay, or are there any difference between the observed number and the expected number? That is the matter of study. Our theory is saying that in a particular sample of size n, this should be the expected number of stomach cancer patients. And when I am gathering the sample, I am observing that this is the number of patients having stomach cancer. So this is called observed frequency, and this is called the expected frequency. So we have got for each of these samples, first sample, second sample, third sample, we have got this particular thing. We have got observed frequency and the expected frequency. Observed frequency is denoted by capital Ni, expected frequency is denoted by small ei. Now, when step number 4 is that after gathering all these information, the step number 4 is that when we if we assume that the null hypothesis is true, and under the assumption that this null hypothesis is true, we expect, what do we expect? As I just now have told you, we expect that this observed frequency must be close enough to the expected frequency. That is our requirement, that is our expectation. It has to be. If your data is such that your observed frequency is very close to your expected frequency, then your data is super fine, and the persons who have collected the data, they are, I mean, I must say, they are super agents. They are unbiased, they have done their parts very correctly. But this is not always the true, because we are not the honest people. Okay, statisticians, very stalwart statisticians are there who can manipulate their data, so which is very illegal. So therefore this is not always close, but it is expected to be close to ei. That is when the null hypothesis is true. The quantity ni minus ei whole square should not be too large. Now, what is this ni minus ei whole square? You know that whenever we consider the observation xi and the mean x bar, we do not actually consider their deviation as xi minus x bar. Rather, what we do, because in the deviation, some positive values and some negative value may arise. Sometimes this capital Ni is less than small ei, and sometimes this capital Ni is greater than small ei. So some positive values and some negative values may come theoretically. And if they come theoretically, it may also happen that your positive values are canceling your negative values, isn't it? So there is a provision of happening this kind of thing, which we want to avoid. So what we actually do, and if it is mean, if I am calculating the deviation of observations from mean, then there is a very well-known theory which says sum of the deviations from mean is always 0. Although these EIs are not means, anyways, in one sense it is mean. This is because it is the expectation of something. Anyways, it may be 0 or may not be 0, but we want to avoid this kind of scenario. So we always do, what we always do, we always try to take the square of the deviations. So the square of the deviations have been taken, and the square of the deviations will be very small if Ni and Ei, they are too close to one another. Okay, the chi-squared statistic in that respect is given by this. And what was the original formula of chi-square that I told you about? Suppose I'm writing over here. There are, suppose, standard a small k number of standard normal variates, z1, z2, zk, then z1 square plus z2 square plus ... plus zk square is a chi-square variate with k degrees of freedom, isn't it? So from this general formula, general theory, somehow and this process is not beyond the scope of our syllabus. This test statistic has been designed. So what we are actually about to remember is, this is the test statistic, the square of the deviations of the difference of observed frequency and the expected frequency, and its ratio in relation to expected frequency will be calculated for each case of the sample size I, and all these values will be added together. All these values will be added together, and after that what we will do, we will reject our H naught when our this TS. What is this TS? This, okay, I have not mentioned what TS is, because you probably were thinking that we are learning chi-square, or from where this TS is coming. TS is a very general term. It's the abbreviation for the word test statistic. Statistic means sample measurement. Sample measurement, that is called statistic, isn't it? And any sample measurement which is testing your hypothesis is called, any sample measurement which is testing your hypothesis is called test statistic. In this case, the test statistic is chi-square. Yes, yesterday we did TS, where TS was students T. In the last week we did TS, where TS was Z, and so on. So you can, if you have any problem, you can write the word chi-square over here. No problem with that. Okay. So this test statistic is given by this, and after that, what is the criteria for rejecting this null hypothesis? The criteria for rejecting this null hypothesis is, that if TS is sufficiently large with respect to what? With respect to a tabulated value. Okay, students, then I'm going to show you something. Okay, just hold on a second. Probably I don't know what mode of tool you are using to attend my class, but if you are attending your laptop or your desktop, probably you will be able to see it. If you are using your mobile phone, that it would be a kind of tedious for you to find out the statistical chart that I actually shared with you. Let me open that statistical chart. Okay, it's opening. Just hold on a second. Okay, I'm going to reshare the thing once again. It's taking some time. Just a minute. I don't know whether you are able to see my screen or not. In the statistical chart, it's not opening. I don't know why. You have the statistical chart, you will be able to see that there is a chart which is meant for chi-square statistic. The chi-square statistic. Now this chi-square statistic, in above, if my chart is not opening somehow, I don't know why. If you have this chart with you, you'll be able to see that on the column headings are level of significance given. Now you already know what level of significance is, and on the left of the chart, the row headings are the degrees of freedom. Now, if you are drawing the K samples, your degree of freedom will be K minus 1. So at K minus 1 degree of freedom, you are going to test the tabulated value of chi-square. You are going to test the tabulated value of chi-square at K minus 1 degrees of freedom. So just like we did in case of T statistic, just like we did in case of Z test, we are going to test our calculated value of TS with respect to tabulated value of chi-square. If the TS is more than my TS, my calculated value is more than the tabulated value at the specified level of significance, do not reject, you reject H naught. You reject H naught. If we always do so, if calculated value is larger, we reject H naught. So we reject H naught. And if your calculated value is less, we fail to reject H naught. Okay. So you just see a semicolon type of thing over there. So this right, the sentence, you just don't mix it up. We are going to reject this when TS is greater than the tabulated value. We are going to accept when TS is less than the tabulated value. So these are the steps that we are going to use for the chi-square statistic. Now the situation that has already been discussed with you, we are going to present the situation in terms of a problem. The problem is, suppose in the above problem of blood types and cancer, that a random sample of 200 stomach cancer patients yielded 92 having blood type A, 20 having blood type B, 4 having blood type AB, and 84 having blood type O. Now their sample size is 200. It is a large sample. And from this 200 of sample of stomach cancer patients, actually they have collected all the stomach cancer patients from here and there, and they are studying their blood types because they are interested in studying, in knowing the blood types and their relation with the stomach cancer. Now these are the observed frequencies. 92 is the observed frequency. These 92 people are having blood type A, and they are suffering from stomach cancer. 20 people are having blood type B, and they are suffering from stomach cancer, and so on. Yes, the significance at 5% level of significance that enables us to reject null hypothesis that the blood type distribution of stomach cancer suffers is the same as that of the general population. Now you see, I have not written the null hypothesis over here, but you have to, in the solution part, you have to write the null hypothesis. The null hypothesis has already been written earlier. So since I have not mentioned it over one again, but for your sake of understanding, let me write it properly. So my null hypothesis was capital P1 equal to 0.41, capital P2 0.09, capital P3 0.04, and capital P4 is 0.46. And my alternative hypothesis was Pi not equal to P small pi for I equal to 1, 2, 3, 4. This was the null hypothesis. Under the null hypothesis, we are going to test. These are the observed frequencies, as I have just told you. So I have mentioned the observed frequencies over here. Expected frequency, you already know how to calculate this expected frequency because your variable is a binomial variable. So expected frequency will be the sample size multiplied by the respective probability. So 200 into 0.41 is 82. 200 into 0.09 yields 18. Now you see that the important part is that I expect 82 people having stomach cancer and blood type A. While in the observed case, I am finding 92. I expect 18 people in here. In actual case, I am finding 20. Here I expect 8, but here it is less. Here I expect 92, here it is less. So sometimes more, sometimes less. Okay, but the values are, these difference is 10, this difference is 2. Okay, so I want to test. This is the thing that I'm actually trying to relate the theory that you have just learned with the calculation. Okay, sorry. Now, anyways, so once we get all these things together, after that, now we are in a position to calculate the test statistic. My test statistic, as you can recall, the formula was, just a minute, what is that? I hope you are able to see my screen. Okay, I'm enabling the chat box. So please write, you can write your roll numbers in the chat box. So now you see what my formula of chi-square, or my formula of test statistic was summation I goes from 1 to k ni minus ei whole square by ei. Now what they are doing, how many i's are there? 4 i's are there. So I will run from 1 to 4, ni minus ei whole square by ei. Okay, now they are taking the differences of these two. So we are getting 92 minus 82 whole square by 82. 20 minus 18 whole square by 18. I can see 45 people present, but only 26 participants have given their attendance. Please, others, write your roll numbers in the chat box. Probably they are not attending class. That means they are just they have just opened the portal and they're doing something else. So from there also I can find some ratios who are attending and who are not. Anyways, it's up to you. So oh my god, what is happening? So in this manner we have calculated TS and the TS has come out to be 4.1374. Okay. Now you go to the statistical chart. My statistical chart has not yet opened. If you have the statistical chart with you, you open the statistical chart and you will find my sample size is how much. Now this is the case. This is the case. One thing that you have to keep in mind, this size, it was written, remember, I didn't mention that chi-square follows the degree of chi-square is associated with the degree of freedom n-1. N is the sample size. I associated chi-square with the degree of freedom k-1. K is something different. K is the number of variables that are present in the null hypothesis. How many variables are present in the null hypothesis? 4 variables are present in the null hypothesis. Capital P1, capital P2, capital P3, and capital P4. So your K should be equal to 4 and not 200. Remember this. Okay. So therefore, in the theory, in the definition, K-1 is mentioned. K and N, they are not same. Now at 4-1 means 3. So at 3 degrees of freedom, your tabulated value of chi-square at 5% level of significance is 7.815. Our test statistic 4.13, which is less than 7.815, and we know if the test statistic is less than 7.815, then we fail to reject the null hypothesis. Okay, at 5% level of significance. And therefore, if it is so, then my null hypothesis, I'm going to accept it, and my conclusion will be that the blood type distribution of people with stomach cancer is the same as that of the general public. Okay, so there is some sort of relationship between the existing blood types and the blood types and the stomach cancer. Remember, the population, there are various types of people. There may be people who are having some sort of blood types which are very unknown and atypical. Okay, it is not like AB positive, AB negative, B positive, B negative, and O positive and O negative. Other blood types are also rare. Blood types are also there. So you have to, but we want to connect whether these blood types are responsible for stomach cancer or not. So that is the point of study, and we find that yes, they are responsible. The existing blood types are responsible. So let's meet in the second session.